Okay, so yeah, I'll just talk about Jindalee's Magnesite project, but it's mainly going to be around the magnesium industry, magnesium compounds, just to kind of follow on with the theme of today's talk. Usual disclaimer there, don't believe too much of anything I say. So a little bit of background on Jindalee. It's been around for quite a while, listed in 2002. Still a very tight capital structure, as you can see, only 35 million shares on offer, and yeah, market cap around 9 million at the moment. Several previous successful spin-outs, Energy Metals, the tenement package that underpinned Alchemy, and also Anchor. We've currently got $3 million in cash and stakes in a few companies there. We've got quite a few projects you can see, mainly in WA. The one I'll be talking about today, Prospect Ridge down here in Western Tassie. But we've got projects that cover a whole range of commodities, non-managed JV and iron ore there. Diamonds project up here in the Kimberley. We've got the kind of western side of the Pioneer Dome that David was just was talking about earlier. A few gold projects, and down here around Widgie area, sorry, further south down here, and also a vanadium project. So we're kind of covering a few bases there. But today it's the Prospect Ridge project I'll be talking about. As I mentioned, I'll start off talking about magnesium and magnesium production and so on, and kind of in a roundabout way get to magnesite and then the Prospect Ridge project itself. Okay, so magnesium, it's very abundant. It's the eighth most abundant element of the solar system, in the crust and also in seawater, which underpins a few of the industrial processes that magnesium metal is actually sourced from. Pretty much all of the geologists among us will have seen magnesium in various minerals and in some very common minerals, as well as in salts, brines, and in it's currently mined, sources of the magnesium currently mined: dolomite, magnesite, which Magnesium Oxide, and the hydroxide. Despite this, abundance of magnesium in various forms, it remains on the European Union's critical minerals list. So the most up-to-date critical minerals list, just released in October, still had magnesium on it. Magnesite was actually on the list in 2016. The reason for that was, as some of the speakers, or John in particular, mentioned right at the beginning of the day, 95% of the consumes comes from one source, being China. So they view it as critical in terms of their supply, or the concentration of supply. It's used primarily in alloys and die casting, some in the Kroll process, producing titanium from the chloride, and in steel desulfurization. It's getting increasing use in the alloys and die casting, so phones and so on. It's probably why phones burn so well nowadays. And I guess, again, with this kind of increasing interest in EVs and so on, you need, for a nice EV, you need as light a vehicle as possible. So magnesium alloys, aluminium magnesium alloys, increasing use of those will be important in reducing the weight of vehicles. So there's some predictions there of a considerable increase from 4 to 5 kilos in vehicles currently up to 140 kilos. So that's significant growth if that comes about, leading to pretty important weight reduction there. Okay, so to produce magnesium, currently there's about 1 million tonnes of magnesium metal being produced annually. That grew very rapidly around the 2000 mark, and again you can see the the dominance of supply coming from China. So the magnesium industry in many countries was pretty much destroyed due to the rapid growth of low-cost production from China. Many magnesium producers basically went out of business, despite a large number of trade barriers and so on being erected to try and save those companies. And again, as I mentioned earlier, 95% of European supply is from China. It's produced predominantly from the chloride via electrolysis. There's a few different routes, but that's the dominant kind of process that's used. But there are direct reduction pathways using magnesite or magnesium oxide using various reductants. So we don't have any magnesium currently being produced in Australia. There was a pilot plant that did produce about 300 tonnes in Queensland around 2000, but the full-scale facility that was planned didn't ultimately go ahead due to various cost overruns and complications scaling up the technology. There were, at the same time, I guess Australia had that kind of mini magnesium boom, and there are a number of other proposals, pretty much one in every state, that would have actually doubled global production. So it's kind of no surprise that not all, but actually unfortunately none of those went ahead. They included smelters in South Australia, here in WA, and the one that was proposed for Tasmania actually used, or was proposed to source its magnesite from Prospect Ridge. So as well as the magnesium itself, there's a huge magnesium compounds industry, and for a range of purposes, for feed supplements, in a whole range of chemical processes, construction. Magnesium hydroxide is, one more. Yes, so magnesium hydroxide particularly useful in water and waste treatment purposes. The advantage is it say for acid mine drainage and so on, you never get a kind of overrun on your pH. It doesn't actually, it's almost self-buffering. You'll only end up with a pH around 9 rather than, if you keep adding lime to solve a pH issue, sometimes you can create another problem going the other way. Also, it doesn't result in a whole lot of or less precipitates, so you don't end up with a great big pile of sludge. So, and the other increasing use for the hydroxide is in flame retardants. So the primary sources for a lot of these chemicals are chlorides from brines, so bitterns, sulfates again from salt sources, and the carbonate. So the oxide is the principal input for various magnesium compounds. It's kind of the primary feedstock, which ultimately is sourced from magnesite, basically because it's a lower cost than coming from brines. So there's some very simple chemistry involved. In fact, there's pretty simple chemistry for most of the magnesium compounds. So magnesium oxide. What do you do with it? So there's two main things that people do with magnesia. You use this caustic calcining process where you heat it up to 850-ish kind of degrees, and you end up with your kind of agricultural grade, chemical grade kind of products. And there's an increasing need for those kind of compounds, or increasing demand. Sorry. And then the second process, or second kind of route that the magnesia ends up in, is in what's called dead burned or electrofused magnesia. It's basically heated up in a kiln at higher temperatures for longer periods of time, to get refractories. So for blast furnace linings, that kind of thing, or kiln linings. And these kind of dead burned and electrofused magnesias, you end up with a higher mag oxide concentration. Sorry, poor word, but what you're really getting is this nice, strong, interlocking crystalline structure. You get reduced reactivity of the mag oxide itself, higher density, larger crystal sizes, and so they're brilliant for things like lining furnaces and so on, or my mum's kiln out the back when she was into pottery, fire bricks, etc. Despite the fire bricks, she did manage to burn the shed down. So it's not foolproof. Okay, so magnesite, it's kind of like the key starting point in that magnesium compounds industry, and it's found in four main kind of deposit types. You get chemical kind of precipitates in lagoons and salt and freshwater lakes, and so the deposits, Lee Creek in South Australia are examples of that, nice bedded deposits. You get hydrothermal alteration of olivine and serpentinites, and vein filling, say around ultramafics. I'm sure many people have, walked over magnesite in ultramafics here in WA. And the last one, which produces, pretty large deposits, including the Prospect Ridge deposit, is through replacement of dolomite or limestone by magnesium-rich fluids, so typically, mag chloride. And then, as a result, you do get gradational contact. So you'll move from, say, a pure limestone through a dolomite and then into the magnesite itself. Magnesite production, about a year ago, about 28 million tonnes per annum, predominantly also from China. Whereas in Australia, our production is very low, under 1 million tonnes, with, very small amount from South Australia. Pretty much all this production comes from Queensland, or QMag. They're now owned by a Belgian company, Sibylco. And they've got huge deposits, over 1 billion tonnes at 42 plus % MgO. And so these are the top 4 Australian deposits. Second one, Archer, who have the Lee Creek deposit I mentioned earlier. Jindalee, so our deposit, the Prospect Ridge one we just recently released inferred resource, 25 million tonnes there. And then there's the fourth one on the list is Corab, who've got a deposit at Bachelor. As I mentioned, there's various occurrences here in WA, mainly associated with ultramafics. QMag, as well as producing just the magnesite itself, they actually do have some production of secondary products. So they do calcining and so on to produce magnesia products for both chemical and the refractories industries. Okay, so just Prospect Ridge itself, just located there in northwestern Tassie. It has been known for a long time. It was first kind of stumbled over by survey geologists in the 20s, and then a lot of work was done on it by CRA and Mineral Holdings Australia in the 1980s, and who produced or defined the first resources and significant resource potential. Then a number of PFS type studies were completed by various parties up to the point, or initially by Crest, and Xstrata made them an offer, which for some reason they chose to refuse. And then the project has basically stalled since then, unfortunately. The project was kind of covered by retention licences, which mine makers purchased. Some further studies were done by Beacon Hill, who ultimately, decided to relinquish the ground. So I guess Jindalee's been fortunate in we were able to peg the project completely as open ground, but having the benefit of the vast volume of studies that have been undertaken over the the project. Sorry, I'll just flick back to that previous map. It kind of gives you a better idea. So the project is situated on I guess this Arthur lineament, which is a belt of metamorphosed rocks that extend basically from the coast all the way through our project, down through Savage River and so on. And we've got the magnesite, in the centre here, this kind of pinkish colour, and there's steeply dipping metasediments and amphibolites basically either side. And there's some more recent cover, so there's some Permian, glacial sediments and recent alluvium that also obscures some parts of the project. The deposit itself is pretty much massive magnesite with minor dolomite and talc, and in the hanging wall there's these quartz mica schists and amphibolites and pearlites in the footwall. The nature of the deposit kind of lends itself to some kind of karstic weathering features and some solution cavities within the magnesite itself, but in essence it's just a great big slab of magnesite. Most of the drilling you can see here that we were able to use in our resource estimation was completed by CRA, Crest and then Beacon Hill. Okay, so we've been able to move things forward pretty quickly, pretty much just leveraging the existing data. So as I mentioned earlier, 25 million tonnes at 42.4% MgO. There's no reason that we can't significantly expand that considerably beyond that number. There are lots of previous, internal kind of resource calculations by the CRA, etc. And just given the fact that our resource only extends to 100 metres depth, but drilling goes down to over 300 metres, it's pretty much a continuous slab of magnesite. The resource again, it only goes on 1 kilometre of the 3.5 kilometre strike of the project. And if I just flip back here, you can flip back. Sorry again. So Arthur River itself, you can see that's the area covered by the resource. There's another deposit down here at Lyons River where, so again, some previous internal estimates were completed by the previous owners. So there's no reason to believe we can't significantly expand the scale of the resource. But the main thing, I guess, as with most of the industrial type products and many of the products people have talked about today, is that the issue isn't really about scale. It's more about what can you do. What does this suit a specific end user and so on. So our effort it's mainly focused on the metallurgy. So having some quite good success in being able to float off some of the separate out the deleterious elements. In this case, it's silica bound up in the talc, and produce a higher grade product. And then once we do that, the idea is we will just have a lot of samples we can go and take around the end users to see if they can actually produce something that's useful for them. And we're talking to various groups, both here in Australia, but also in the US. I guess we've also been, as well as the previous studies, we've also benefited considerably from the Mineral Resources Tasmania. They've had a fantastic core library there, which we were able to access, and so the met work's all been done on historic core that was beautifully stored, and they were even able to cut it up for us. So just have to acknowledge that as a great organisation, very, very helpful. So yeah, we're just about to finish the met test work, and then basically we see the opportunity is to either produce calcine material, probably not for us, the dead burn magnesia, and obvious opportunity to grow the resource and mining lease application is probably the next thing to make sure we can keep moving it on. So that's it.